Hello everyone, welcome back. In this last video of the ANOVA chapter, we're going to talk about a multiple comparisons procedure, okay, and how it sort of moves us forward. So in the last videos, the previous three videos, we talked about an ANOVA, okay, and what it does. So it's a hypothesis test, or at least how we viewed it is a hypothesis test, which is a generalization of a two-sample t-test. And it can tell us if there are differences between the groups, but it doesn't really tell us which groups are different. Okay? So I call that here an overall test. That may not be a common term, but it's what I'm going to use. Okay? And so if you don't like it, you can blame me. That's okay. But this is an overall test in that we know there's at least one difference somewhere. Okay? That two of the group means are different, right? But we don't know which ones are different. And so certainly we would like to know. So what we need to turn to is a multiple comparisons procedure. And so what we want to do is we want to look at those pairwise group differences. So we're going to use a multiple comparisons procedure to do that. Basically, it's going to be like doing a bunch of two-sample t-tests for each of the groups, okay? Each of the group differences. And so for the example that we had in the last video, there were 5 different groups. And so we're going to do group-wise differences for each of the groups. So we're going to compare 1 to 2, 1 to 3, 1 to 4, 1 to 5, 2 to 3, 2 to 4, 2 to 5, 3 to 4 and 5, and 4 to 5. Okay? And so we don't need to do the flip of each one. We don't need to compare 5 to 1 because it's going to be the same as 1 to 5. Okay? So for the 5, we're actually going to do 5 plus 4 plus 3 plus 2. There's going to be a lot of comparisons in there, and you'll see that in the next slide. Okay? But it's going to be basically a bunch of two-sample t-tests, but there are a few key differences. And those differences make a big effect theoretically, but right now for you'll probably look at them, because we're not going into theory, you'll look at them and say, well, we just did a bunch of two-sample t-tests. That's not true, okay? But you can think of that and go on with your life and not be so totally wrong, all right? So this is what our book defines as a multiple comparisons procedure. In general, they are a set of methods that compare pairs of means with a set confidence level that apply simultaneously to the entire set of comparisons rather than to each separate comparison. Okay? And so that in there, in that long sentence, lies those important differences. So basically, what this is saying is that we have to change our method slightly to deal with the significance level. Okay, so there are theoretical reasons that if you think about hypothesis testing or hypothesis testing, if I use the same significance level for each separate comparison and sort of view them as independent, things are going to go wrong theoretically. Computationally, they'll be fine, but theoretically, they will be not so good. And so that's where I'm going to leave it. If you want to talk about that further or don't understand, I'd be glad to talk about that with you. Okay, so the multiple comparisons procedure that we're going to use is called Tukey's HSD, or Tukey's honestly significant difference. Okay, Tukey's honestly significant difference. There are many of them. Okay, so there's one named for Bonferroni, there's one named for a bunch of people. We're going to use Tukey's HSD. Okay, and so when you perform Tukey's HSD on the example that we saw last time, you get this. Okay, and so you'll see there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so out of the 5 samples, or the 5 different groups, we come up with 10 different pairwise comparisons. Okay, so you'll see these Tukey multiple comparisons of means for 95% family-wise confidence level. So you see that is confidence interval speak there, okay? But it's not just a regular 95% confidence interval. It's a 95% family-wise confidence interval. And that family-wise is trying to control for what they call the family-wise error rate, or some people will abbreviate that as the FWE, okay? And so these intervals that you'll see down below and then the p-values are going to be adjusted in such a way to control for the error rate. All of that makes no sense to you, and that's fine. I just need to say that for posterity reasons. Okay, so you'll see down here that we have each of the samples. Okay, each of these pairwise differences, they give you the actual difference in that first column. Okay, and then they give you in the second and third columns the lower and upper bounds of a confidence interval. Okay, for in fact a 95% confidence interval that controls for the family-wise error rate. Okay, so they give you a lower and upper interval there, and then they give you an adjusted p-value. Now you can use either the interval or the p-value to make your decision. Okay, whichever one that you prefer. So if you look at the interval and 0 is contained in the interval, then you can't conclude that there is a difference. Similarly, if the p-value is going to be greater than 1 minus that family-wise confidence level above, then, or rather, you don't have to worry about the family-wise confidence level above. You just compare that to whatever alpha that you're using. Here it is 5%, which is 1 minus 95%. Okay. If the p-value is larger than that significance level, then you would again fail to reject the difference. Okay. So, sample. If you look at the first line, you'll see that sample 1, 0 is contained in the confidence interval, and the p-value is larger. Okay. Then there is you can't conclude any difference. Okay, you can't conclude a difference between sample 1, group 1, and group 2. You don't have to look at the confidence interval and the p-value because they're going to make the same decision. Okay, so you don't have to worry about both confidence interval and the p-value making the same decision. So you'll see that 1 and 2 are different, but if you look down at 1 and 3, they are very different. Okay, the interval does not contain 0 anywhere close, and the p-value is very small. It doesn't even register as different from 0. Okay, so you can go so on and so forth, look at all 10 comparisons, and then come up with a few sentences that describe what's going on here. So those are confidence interval. That's a hypothesis test p-value there. Okay, the inference that you get, what you get out of these, at least what I see, is that a group 3 is different from all other groups. And so if you look wherever group 3 is in these pairwise comparisons, the p-value is either 0 or very close to 0. So 3 is different from all other groups, which if you go back and you look at the plot is very evident there. Okay, 4 is different than 2, and 5 is different from 1 and 2. Okay, and so that sort of sums up all the pairwise differences. So ANOVA told us that there is a difference, at least somewhere. And then the multiple comparisons procedure tell us where those differences are. Okay, and so that's where I'm going to stop for now. And I will, I guess, not talk to you again in video form before the final.